Hi guys, I figured I'd just make a solution video for this test since it was a little bit harder and required a little bit more like weird application thinking stuff. So I'll just go through all the problems one by one. Okay, problem one was this integral. So if we factor the top, then we don't get an x plus 3 factor. So we can't cancel this out, which means we have to try using long division. So x plus 3 into x squared plus 4x plus 5. So this goes in x times, we subtract x squared plus 3x, we get x, bring down the 5, this goes in 1 time, minus x plus 3, we get 2, so we add 2 over x plus 3. So now we can integrate 0 to 3 of x plus 1 plus 2 over x plus 3 dx, which is the same as integral of x squared over 2 plus x plus 2 times the natural log of absolute value of x plus 3. 0 to 3. So we plug in 3, we get 9 halves plus 3 plus 2 times natural log of 6. Subtract. Then we plug in 0, we get, these are both 0, so we just get 2 times natural log of 3. So these combine to make 15 halves, and natural log of 6, natural log of 3. Subtract them, you get 2 times the natural log of 2. And that was C. Okay, so for number 2, when you see something squared or any sort of even degree in just numerator, and you have like a constant in the denominator, you see this, and in the numerator you just see a constant, and you want to try completing the square. So to do this, you do x squared plus 4x plus 4, integral, so under 1, x plus 2 squared, so that gives us x squared plus 4x plus 4. Then we have a 9 left over, plus 9 dx. We can pull out our 1/9. 1/9 integral 1 over 1 plus x plus 2 over 3 squared dx. So now we have a sort of tangent form, inverse tangent form. So we let u equal x plus 2 over 3, so du equals 1/3 dx. So we multiply this by 3 when we switch to du. So we get 1/3 integral of 1 over 1 plus u squared du, which is 1/3 tangent inverse of u plus c, which is 1/3 tan inverse x plus 2 over 3 plus c. Okay, so for this one, a and k are constants. And what you have to notice is something like this and something like this, you have to be able to recognize, oh, you have this term down here, and the derivative of this whole term would be this term. So here you want to use u sub. So we let u equals a minus e to the negative kx. So du is going to be e to the negative kx times dx. So when we plug in du, we're going to cancel that out. So we're going to end up with an integral of 1 over u times e to the negative kx over e to the negative kx. That just turns into 1 du, which is equal to natural log of u plus c, which is equal to the natural log of a minus e to the negative kx plus c. Okay, for 4 we need to find the relative maxima and minima of this function f. So we do this the exact same way we did things in earlier units. We just take the derivative and look at the sign chart. So you take f prime, and we can do product rule. So we get 3x squared e to the x plus x cubed e to the x. Just to make it easier, I would factor x squared e to the x, 3 plus x. So this way we can instantly see that our two zeros are going to be 0 and negative 3. So we can create a sign chart with x down here, f prime of x right here. So we have negative 3 and 0, and at both these spots f prime is going to be 0. And notice this is a double root, so there's no sign change. And here this is a single root, so it's a sign change. And if we just look at this side as x approaches infinity, then this is just going to approach infinity, so it's positive. No sign change, this is positive. Sign change, this is negative. So this is going to be a maximum, right? Or excuse me, not a maximum. Okay. A minimum. Yes, because on the right you have a positive slope, on the left you have a negative slope. So it's going to be kind of like the dip of a parabola. Whereas here, since it's positive on both sides, it's just going to be an inflection point. It looks something like that. So we don't care about this point. So the only relative maximum or minimum that we know of is going to be this point here. So we know it's x equals 3, negative 3, so we can plug it back into the original equation, and we get negative 27 over e cubed. So our relative minimum, I don't know why I keep saying maximum, at the point negative 3, comma, negative 27 over e cubed. Okay, so for this problem, the first thing we need to do is find f of 2, which is what it asks for. So that'll end up being 1/4 times 16 plus x squared is 4 minus 3. And that'll end up being 5. There's part 1. Now we need to find g prime of 5. Well, g prime is f inverse, so we need to find the slope of the inverse function at this point. So we can use our formula, f prime of x is equal to 1 over g prime, since g prime is that, of f inverse of x. And we already know that here we're just looking for 5, and here this will end up being 2. So f prime of 2 is 1 over g prime of 5, which means that g prime of 5 is just 1 over f prime of 2. So we can find f prime of 2 pretty easily. So f prime of x is x cubed plus 2x. So f prime of 2 is 8 plus 4 equals 12. Therefore, because of this, g prime of 5 is equal to 1/12. Okay, for this integral, you again just sort of have to notice that you have a natural log and you have a 1 over x in there, so there's going to be some sort of u sub. So we can try, since natural log is the thing being quinth, raised to the 5th, let u equal natural log of 4x. So du equals 1 over x dx. So that's pretty easy. So then we end up with the integral u to the 5th times x over x. So those cancel, du. Then we just have integral of u to the 5th equals 1/6 u to the 6th plus c, which is 1/6 natural log of 4x to the 6th plus c. Alright, for this integral, it looks a little bit ugly, but so a is a constant, and again we have to see we have a cosecant and then we have a cosecant cotangent, and negative cosecant cotangent is the derivative of cosecant, so there's going to be some sort of u sub. So we don't want to just let u equal cosecant because we also have an 8 here and we don't want to end up with like 1 over u plus 8. We can do that, but it's a lot cleaner to just do let u equal cosecant ax plus 8, because then the derivative is the same as just regular cosecant. So du is going to be negative a, because of chain rule, cosecant ax cotangent ax dx. So integrate that. The cosecant and the cotangent are going to cancel. So we're going to be left with just a negative 1 over a times the integral of 1 over u du, which gives us negative 1 over a natural log of of u plus c, which is negative 1 over a times natural log of cosecant ax plus 8 plus c. This one's pretty straightforward. You just have to break it up into 3 pieces and use exponent rules. So this is going to be the same as integral of e to the 5x over e to the 13th x dx plus integral of e to the 2x over e to the 13th x dx plus integral of 5 over e to the 13th x dx. So when we have e to the a over e to the b, it's equal to e to the a minus b. So we can rewrite all of these as this one would be e to the negative 8x dx plus e to the negative 11x dx plus 5 times integral e to the negative 13x dx. So now this is pretty straightforward since it's just e to the kx. This is equal to negative 1/8 e to the negative 8x plus negative, or I guess you can do minus, okay, minus 1/11 e to the negative 11x minus 5/13 e to the negative 13x plus c. Okay, so for this you can just do a simple u sub of let u equal e to the x, because that'll mean du is equal to e to the x dx. So the ex here will just cancel. So we're left with secant u du. And as you should know or have memorized, this is equal to natural log of secant u plus tangent u plus c, which is equal to the natural log secant e to the x plus tangent e to the x plus c. Okay, for this one we just need to find f prime of x. So the easiest thing to do first is to split this up using log rules. This will be equal to the natural log of sine x minus natural log of x squared minus e to the 4x minus 7. And this is good because this is much better than having to do quotient rule with this sort of function. So then we can take f prime x, and since derivatives distribute over addition, this would become sine x in the denominator times the derivative of sine x, which is cosine x in the numerator, minus, then the denominator will have x squared minus e to the 4x, this is badly written, minus 7, then the numerator will have the derivative of that, which is 2x minus 4e to the 4x, and that's it. And you can turn this into a cotangent, but it doesn't matter, so. Okay, this one is interesting. So we definitely want to use logarithmic differentiation here because this is extremely ugly, and it would take like 2,000 pages to actually write it out. So cross out with y. So natural log of y is equal to 1/5 natural log of x plus a, x plus b over x plus c cubed, which is equal to 1/5 natural log of x plus a plus natural log x plus b minus 3 natural log of x plus c. So then we can take the derivative of both sides, and we're left with 1 over y dy dx equals 1/5 1 over x plus a plus 1 over x plus b minus 3 over x plus c. So then we can just multiply both sides by y, which is that ugly thing. So dy over dx is equal to 1/5 times the 5th root of x plus a x plus b over x plus c cubed times 1 over x plus a plus 1 over x plus b minus 3 over x plus c. There you go. Okay, so for this one, you can use logarithmic differentiation, but you don't need to. It's a lot quicker if you don't. You can just use the exponent rule, which says that f prime x, since our base is 3, it's just going to be nothing but 3 to the tan of 7x still, x, times natural log of 3. Then we also have to do chain rule because it's just like e to the u. We have to multiply by the derivative of tangent of 7x, which is going to be 7 secant squared 7x. And you don't have to simplify it, so that's it. Okay, so for this function, we do a similar thing. Since we have log base 7, we're going to have, for f prime of x, we're going to put this in the denominator. Square root of 5x cubed plus x under 1. But then we multiply by 1 over natural log of 7, because we have log base 7. But we also have to do chain rule for this, which is going to be 1 over 2 root 5x cubed plus x times derivative of this stuff in here, which is 15x squared plus x. Yeah, plus 1. Yeah. So there you go. Okay, on this one you have to be a bit tricky. I even got this one wrong because I wasn't thinking very well, but you cannot use the exponent rule here because the base is not a constant. So you have to use logarithmic differentiation. So I'll make that a y. So natural log of y is going to be natural log of x raised to the x squared, which is the same as x squared of natural log of x. Nice. So take the derivative of both sides, 1 over y dy over dx. We use product rule here, so 2x natural log x plus x squared times 1 over natural log of x times 1 over x, because we have to take chain rule for the natural log of x in addition to doing the natural log of natural log. So we end up with 1 over a natural log of x times the derivative of natural log of x. So we have this. And then simplify, we have dy over dx. Bring the y back over here. We have equals natural log of x to the x squared times 2x natural log of x plus, and you can just cancel these out just to make it look nicer, plus x over natural log of x. And that's very ugly, but that's okay. Okay, so for part B, we need to find how much of the Piazza Posium is left after 75 hours if we begin with 500 grams. So if we want to write an equation for P of T in like terms of grams, then we have our initial amount, 500, times e to the negative, our k is natural log of 2 over 8, so natural log of 2 over 8 times t. So we need to find P sub g of 75. That'll just be 500 e to the negative 75 natural log of 2 over 8. And you don't have to simplify it because I have no idea how to simplify that, so there you go. Okay, 16, we need to find the arc length of this whole function. So first we remember the formula, and go from a to b with the square root of 1 plus dy over dx squared dx. So we need to find a and b, because I guess we can go ahead and find dy dx first. Dy dx is just going to be 1 over square root of 1 minus x plus 2 squared. That's pretty easy, right? So I also need to find the bounds. So if we look at the function, we know that regular arc sine think about it, arcsine of, say, 0 is just going to be 0. So we know it passed through here, and we know at arcsine of 1, then we go up to pi over 2, and same thing over here. So it'll look something like that, except this is shifted to the left 2 because transformation x plus 2. So that is not the equation. The graph actually looks like that, sort of, where this is instead negative 1, this is negative 3, and this is negative 2 where it passes through. So all we care about are the x bounds, so it goes from negative 3 to negative 1. So our final equation will be L equals from negative 3 to negative 1, square root of 1 plus 1 over 1 minus x plus 2 squared. And I just canceled out the square and the square root. You don't have to. Dx. And you don't have to solve it. So you just set that up and that's the answer. Okay, we'll do the bonus 2. So for this, it's difficult to see how to approach this. If you have time, I would suggest like noodling around with different stuff. But the thing you always want to try to start with is u sub. And best thing to do is let u equal 1 plus root 2x. So du is going to be 1 over root 2x dx. So we're going to end up integral of root 2x over u du. And this may not look like much because we have an x, but we can see that because u is equal to 1 plus root 2x, root 2x is equal to u minus 1. So we can plug that in here. So we have integral of u minus 1 over u du. And we know how to integrate that. That's just integral of 1 minus 1 over u du, which is the same as integral, or no, not the integral. It gives us u minus natural log of u plus c, which is the same as 1 plus root 2x minus natural log of 1 plus root 2x plus c. And there you go.